Hi again everyone. We're looking this time at a locus in the complex plane that involves the argument rather than the modulus of this complex number. So there's the argument of z plus 2 minus I. Now again we could think geometrically, and to do so I'll want to think of this in terms of the difference between z and a complex number which is negative 2 plus I, so equal to pi over 6. And what I'm really saying then is that the point z, this point here, negative 2 plus I, negative 2 plus I, is the starting point, if you like, or it's the translation of my origin. Now, where is an argument of pi over 6? Well, that would be moving off like this, with an angle pi over 6 here. And where is, beg your pardon, that one was supposed to be pi over 3. No wonder it didn't make sense. So pi over 6 would be there, pi over 3 would be further up. And so we're looking for points which are higher than pi over 6, lower than this, and equals, so including. And so we're basically looking for the space in this section. From that point outwards would be a ray there and a ray there. And that's more or less our geometrical argument of what's going on. Analytically, we do the same sort of thing as we have always done. We name our point x plus y times I. And this time I'll split the inequality into two parts, I think. So let's work first with the argument less than or equal to pi over 3. Replacing z with x plus yi plus 2 minus I is less than pi over 3. Now, when we want the argument of a complex number, well, actually, just before I get to that point, I'll group together the real parts, x plus 2, and I'll group together the imaginary parts, y minus 1, less than pi over 3. So when we want the argument of a complex number, it's the inverse tan of the imaginary part over the real part. Now this looks a bit nasty. We have an inverse tan. Well, what's the opposite of inverse tan? It's to take the tan of both sides. So the tan of inverse tan leaves us with just this. And we have to take the tan of both sides, so we need the tan of pi over 3. Now, that's one of our special triangles. Pi over 3 would be this angle here, and you should remember the ratios of these sides go 1, 2, and root 3. So the tan of this angle would be root 3 over 1. And I have y take 1, and I'll multiply across x plus 2. We're almost there. Root 3x plus 2 root 3 plus 1. So that looks a little bit like the equation of a straight line. It's not an equation, it's an inequality. So if I were to want to sketch this thing, then I would need a y-intercept of whatever this comes to. So that's about 1.7, so that's about 4.4, somewhere up about here. And we'd need a gradient of root 3. So we'd have a line running up like this. That's only part of the story. You're probably happy enough to recognise that that's the lower part of our ray here. And of course this point, which was at minus 2, 1, would exist somewhere along down here on our equation. It should satisfy, of course, if we put negative 2 for x, then that bit and that bit would cancel and we'd leave y equals 1. So the point negative 2, 1 definitely exists on this line somewhere. But the line, of course, goes further than that. Now that was only part of what we had to deal with. We also had that pi over 6 is less than or equal to this thing. So pi over 6 is less or equal to the argument of. Now, everything we did in here with the argument of z will still be true, won't it? So none of this will really change. We will end up with x plus 2 plus y minus 1i. So once again, the tan of this angle would be the tan of the inverse tan. In other words, it would be the imaginary part over the real part. Tan of pi over 6. Pi over 6 is this angle. The tan of this angle is 1 over root 3. Multiplying through, we would have x, over root 3 plus 2 over root 3, and then that would be y take 1, but if I add the 1, so I've got my equation. I suppose it's more typical to write this the other way around. So remember, if I transpose parts of the equation, I reverse the inequality. And what do we have here? X over root 3 plus 2 over root 3 plus 1. So 2 over root 3 plus 1, that'll give me the y-intercept, and the gradient is 1 over root 3. So back to our diagram, we have a different y-intercept and we have a different gradient. But pretty much this will give me the line that runs, which one was this going to be? The higher one or the lower one? So this one will give me the opposite line, and we're looking again for the spaces in between them. Now, I should be able to write this equation into GeoGebra and this equation into GeoGebra that represents the two different parts of my inequality that I was dealing with there. So let's go and try that. I've already marked in our point here negative 2, 1, and so let's get the keyboard going and we'll see how we go with this first one. The first one was y greater than or equal to, and it was root 3 times x. Root 3 x plus 2 root 3 plus 1, if I remember, plus 1. Enter. So there's our first inequality. You can see that it is, I think I might have got the inequality backwards on that one. I did get the inequality backwards. Let's go back and edit that thing. So now, what gave me the clue? Well, the fact that the shading was on the wrong side of the line gave me the clue. So we backspace on that and put a less or equals. Just let me double check my notes there, less or equals. All of a sudden we have the shading on the right side of the line. It's amazing how it helps when you do it, type it incorrectly. Now, we'll type the other equation. This one was y is greater than or equal to. This was x over root 3, x divided by square root 3. Oh, somehow managed to touch that twice. Square root 3, that's better. Plus 2 over root 3. Oh, it's touching twice this this pen. That's it. Cross your fingers, +1, see if this works. Enter. That's better. Now, of course, GeoGebra doesn't realise that I want a combination. I have to type in GeoGebra. I think I have to type this as two separate equations. I've never actually tried typing it all in one. But you can see that these inequalities are labelled A and B. The nice thing about GeoGebra is that I can then go and tell GeoGebra, I want you to go A and B together. So that symbol there is logical connective AND. I'll hit enter on that one. And now if I just hide those ones, there is my diagram showing the origin, I suppose, the translation to the coordinate system. This is our first one with an angle of pi/6. This is the ray with an angle of pi/3. And we were less than this one, more than this one, so we're shading in between. Solid lines this time because the inequalities included equals. So GeoGebra works really well. These lines back here technically shouldn't be shown because we're really only interested in that part there. So GeoGebra forgot to rub those out for us. I guess it's not perfect. And there you have, come on, where did it go? There it is. So there you have a locus, which is, remember, a region of the complex plane defined by this relation here, this inequality, involving arguments this time. We can think geometrically, or we can do the analysis, which a little bit more interesting this time with some inverse tan ratios. That's it for this installment.